So when we're looking at so when we're looking at how the heart's like functioning, right? Like he kind of was describing, like it's a big muscular pump. We're talking about like creating pressure here, right? And for those of you who went through like our physiology class last mod, we put a lot of emphasis on like understanding like different pressures, right? For those of you who are relatively new, easiest way to remember this is when we were talking about like diffusion, right? There's sort of two pressures that are very important inside the human body, right? There are pressure gradients, and then there's like concentration gradients, right? And well, like I said, if you ever want to understand the universe just a little bit better, just understand that nature hates a gradient, you know? And what I mean by that is like nature does not like it when there's like a lot of stuff over here. Like if I just kind of turn this like this and I just go boop, 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 right? If I put a whole bunch of stuff in the corner like this, right? What will naturally happen is that like nature would sort of either push stuff from over here into this in order to like push these molecules apart. If it was like fluid, for instance, like if there was like a wall here separating this, fluid would rush into here in order to like push those materials apart until like the concentration of stuff in here is equal to the amount of concentration of stuff out here. Or more than likely, if it was just empty like this, what would happen is all of these molecules would just kind of go around and like spread themselves out until there's a nice even gradient across, you know, the entire board here. And it would look something, you know, maybe more like this, where it's just kind of evenly spaced, you know, kind of around everything, right? So that's a concentration gradient. When there's a high concentration in one spot and a low concentration in the other, nature will naturally move stuff down its concentration gradient. But obviously the same thing is true of like a pressure gradient, right? Like if I create like an area of high pressure, like let's say, you know, I've got some type of like balloon or whoops, I just closed my PowerPoint. Let's say I've got like a balloon or something, right? Oh no. I don't even know what that was. And I start filling that balloon with air, right? There's a lot less space in the balloon than there is in the freaking, you know, planet that we live on, right? Like, so what's going to happen is as I sort of like put more and more air into that balloon and expands further and further and further, it wants to sort of like rush out of there, you know? And so it wants to rush out here where there's lots of empty space rather than be trapped in the balloon where there's very little space. So that's a pressure gradient. And that's exactly what we're going to see in our heart today, right? Our heart is going to create a pressure gradient by squeezing, contracting its muscle proteins, which will create less space in the chamber of the heart. And then the nature is going to naturally sort of like, oh God, we got to move this out of here, right? And so like it's going to move from an area of high pressure to an area of low pressure. And that's what we're talking about when we're describing like blood pressure and heart rate regulation and things like that. So today, big overview of what we're going over. We're going to look at the structure of the heart. That's probably the most important thing we're going to look at. We are going to talk about functioning of the heart as well as the conduction system, the electricity that makes up our heart. In terms of diseases, we're not going to talk too much about that, although obviously it is very relevant. We just talk about it much more in other classes. And then like disease prevention, treatment, aging, and heart size, things like that. We're not really going to spend a ton of time on that either. So looking at the circulatory system, it is a continuous sort of one-way circuit. That's very helpful in creating these areas of high pressure and areas of low pressure. Like the fact that it is a closed circuit is a big advantage for us biologically. Now, not every animal out there has what's called a closed vascular system, right? So we have a closed vascular system. We have a series of tubes that are basically, you know, all connected in some way or another, right? Like if you look at our vascular system, right, you can kind of see it looks something kind of like this, you know, for the most part. This is a chart, obviously, but like you can see like blood vessels are going to rush out to the heart. They're going to be this like big webbing, but like they're all sort of closed together, right? And the advantage to that is that we are very good at creating areas of high pressure and we're very good at creating areas of low pressure. And that allows us to pump blood continuously around our body. And it makes it very easy for us to regulate things like body temperature and things like that. But not every animal has that. In fact, a lot of animals out there, primarily like insects, are going to have what's called an open vascular system, where it's actually not connected at the end. It kind of just splashes out of these tubes here. The advantage to that is if you're like a freaking grasshopper or a cricket or something, and you make some really big explosive jump and you go flying from here to there, you know, your blood doesn't just pool in one spot. The problem with a circulatory system that's closed is that, unfortunately, if you are moving at super high velocities, your blood will sort of pool in one spot and then it can't get to your brain anymore. And so what will often happen is you'll pass out. And this is why you ever see like the I don't know what the thing is called, but like astronaut circle machine. I don't know what this is called. I'm sure that should be enough to pull up a picture of it though. No, oh man, I mean, there is this is also like a gyroscope, the thing that they, yeah, astronauts will train on this, where they have to spin around like crazy so they can get used to the fact that their brain's probably not getting very much blood, and so then like it can sort of calm down. But I'm trying to find the one that's like astronaut high speed what is that freaking thing called? Oh God, I can't find it. Anyway, it's where they put them in a chair and they just spin them around a room like super fast. And they just pick up more and more speed and stuff. The thing is, eventually what happens is all their blood kind of gets pulled to the back of their brain, but the front of the brain doesn't get anything. So then like eventually they just kind of faint. The same thing happens with like fighter jets and things like that, right? So you know, that's the disadvantage to a closed vascular system or closed circulatory system. But like an open one is really cool because like it's kind of centrally located. So it kind of just splashes blood around the body, delivering oxygen, right? A lot of insects that travel at super fast. G-Force Simulator. Oh my God. Thank you. It kind of just, sorry, I'm very excited that you knew that. This freaking thing, they spin them around like crazy. It just goes through, you know, so quickly. I mean, you can see even in the picture here, it's like they weren't able to capture it properly because it's spinning so fast. And it's great. You know, all the blood kind of pools in the back of their brain, causing them to like pass out and stuff. So they have to like kind of get used to that. And so you'll see like these footages of people just like, and then like, they like eventually kind of faint. If you're traveling at super fast velocities, it's actually kind of an advantage to have an open vascular system, you know? So if you're like an insect that's flying at like 1,000 times your body length in terms of like, you know, distance covered per second, you know, that's pretty fast. So what is great about that is like when you kind of just splash blood everywhere, it can kind of stay there for a little bit and then kind of get sucked back in. So we love our closed vascular system because, like I said, we are able to create areas of high pressure and areas of low pressure using that, which makes us really good at being able to pump body temperature, chemicals, and oxygen and things like that throughout the body really easily. So the heart is going to be sort of what powers this entire system. It's what creates the areas of high pressure and the areas of low pressure because it's got different chambers, some that can squeeze and some that can relax. And so if you do something like this, right, when I squeeze here and I open up down here, this creates an area of high pressure up top and an area of low pressure down below. So blood's going to naturally rush this way. But if I squeeze this way, what's going to happen is that's going to create an area of high pressure here and it's going to send it out. Now, the thing is, when I squeeze this way, this chamber opens back up. Blood wants to rush this way. And that's why you also have like heart valves, and those valves shut. And that keeps blood from going this way. So then it's forced to go out the little tubes that actually send it throughout the rest of your body. So your heart powers this entire thing, right? It's located between your lungs, right in the middle of your body. It is slightly over to the left, which is why we place our hand over the left side of our chest. It is not way over here, though. I think that got started. There's a famous pirate, actually. I was reading a story about how, like, That's one of the reasons why we think the heart is over here. There's a heart symbol. He had like yeah, oh, his Blackbeard. Yeah. He had like, oh no, not that one. That is Blackbeard's thing. I remember that now. But anyway, there was like a very famous pirate that like had a picture of like a skull and like a full skeleton, and the heart was just like over way far to the left. And that's kind of like part of the history there. I'm sure it's not like what originated it, and people aren't getting their anatomy lessons from pirates, but like I'm sure that's sort of what popularized it. So it is a little bit over to our left only because the heart's pretty heavy on one side, and so it sort of tilts like this. That's your left side of your heart, and that's why it's just slightly off over the midline there. So you can kind of see that here, right? It's along the midline for the most part, but this corner is much heavier, so it sort of dips down like that. So your heart is the muscular pump that's responsible for pumping blood throughout the body. It's got several chambers and several different layers. The layers are what create the pressure, and the chambers are what allow that pressure to sort of move around. Now, obviously, your heart is connected when we're talking about the cardiovascular system, right? It is also connected to your circulatory system. It's going to work very intimately with that. And that is all of your blood vessels, right? So your circulatory system is this one-way circuit, right? It's always going to travel, until it eventually works its way back to the heart throughout the body, and allows blood and nutrients and things like that to get delivered to the various tissues of the body, right? And then your blood is the material that your heart is constantly pumping around, right? It's the medium in which nutrients and oxygen and things like that are actually being delivered throughout the body, right? So the heart is in charge of pumping blood around, and it needs the circulatory system, your blood vessels, in order to be able to get it everywhere it needs to go. So blood cells are really cool because they are very good at grabbing onto nutrients and kind of carrying those things around. So when we're looking at the cardiovascular part of things, right, we're going to start by talking about the heart. Now, your heart has a whole bunch of different layers, right? Very similar to muscle here, which makes a lot of sense because, like, remember, heart is made out of muscle. It's made out of cardiac muscle, which looks really similar to your skeletal muscle, but just has a couple different unique things that we're going to look at today. So the heart has a couple different main layers here. The smooth innermost layer is what's known as your endocardium. So when we look at like the innermost layers of the heart, where those chambers are, we're going to see the endocardium. And the endocardium is super, 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 super smooth because we don't want to have any texture on that inside portion of the heart. This is where blood, remember, it's traveling through the chambers, right? So this is where blood's traveling into this chamber right here. We don't want our red blood cells to get stuck on any like interesting texture there, like your blood cells are, when we look at like blood, it is just absolutely a bunch of just little tiny little red blood cells that are kind of running through everything, and white blood cells and other stuff as well. But like, it's just a bunch of this stuff, right? And so like these little things can get caught on the walls if there's too much texture on those walls. So we certainly don't want blood to start clotting inside of our heart. We don't want it to get stuck to the walls there. So that inner layer is extremely, extremely smooth. Then look at this layer right here. And so that's this layer, right? And then look at this one right here. This is called your myocardium. Now, remember when I was talking about muscles, I said anytime you see the prefix myo, we're probably talking about muscle. Well, myocardium is the muscular part of the heart. It's the very thick middle layer that does all of the squeezing, right? This is where contractions are really, like when it comes to a contraction, like this is where the heavy lifting takes place, right? And so we call that cardiac muscle, right? That is our myocardium. Now, it is a little bit different than our skeletal muscle. Like if we look at it, when we look at like cardiac muscle versus skeletal muscle, there's kind of a little bit of a difference here, right? So here's smooth muscle in the middle. This is your organs and stuff, right? This doesn't really have very much contracting that it's doing. You can see how smooth it is. But look at skeletal muscle, right? Skeletal muscle, the stuff that, actually drags your muscles around, has these huge striations, right? Like these really big lines, around the whole thing, because like that's where, actin and myosin proteins are sort of straddle between, right? We see a bunch of Z lines there. And so all those Z lines are, getting pulled. And so it makes these like really big striations that allow those contractions to take place. Remember we were talking about myofibrils, right? Look at all of them. They're huge, and so that's where like a really big amount of like contracting is really kind of getting done. And then look at cardiac muscle. You see how like these are all just kind of like big bundles and they all kind of run parallel to one another. But look at cardiac muscle. They aren't just like running parallel to one another the same way. They're running parallel to one another and they're threaded together. And that's one of the things that makes cardiac muscle very unique. These are all very interconnected, which means if I were to shorten this fiber right here, it's going to kind of drag this fiber around as well. And that's going to kind of drag this fiber around. So you'll notice that there's less striations. It's not lifting as heavy as like, I'm not deadlifting with my heart, like I'm not picking up like a 45-pound, barbell with cardiac muscle, right? It doesn't need to be that strong, but it is very, very, very tightly packed so that when any of your heart contracts, all of it contracts. And that keeps it really in sync together, right? That makes it very good at contracting simultaneously. You'll also notice it doesn't have as much like nuclei, right? If you look at this, like see these little purple ones here, those are your those are nucleuses or nuclei, right? Whereas like you look at your cardiac muscle, there's only one per fiber. And that's going to become really important here in a moment when we start talking about like heart contractions, because like you don't want too many cooks in the kitchen, when you're working with people, you're working in a group to maybe get like some type of group project done. And like one person's like, hey, we should do this. Another person's like, oh, I like that idea, but let's do this. And it's like, no, I really like my original idea. And they're like, no, but I like this one. And then like, there's just like, different things, or like somebody's like, this is the best way to do this. And someone's like, this is the best. It's just too many people, like too many people, nobody can agree. Oh, you know what? I got a better analogy. When you're trying to freaking pick a show to watch on Netflix, right? Like, when you're a group of people and you're trying to decide on what freaking movie to watch, like that can take a full movie's length of time. Like I can't tell you how many times I've been sitting with my roommates and like, we'll like, what if we do this? What if we do that? No, what about this? Like, and then we'd end up watching nothing. Fun fact, my genius roommate, Chuck, came up with a really good system to stop us from doing that. Now it goes in a rotation and like, it's your night to pick the movie and it goes in order. But instead of just picking a movie to watch, you have to give two options. You have to pick two movies that you think would be very good options, and then everybody else votes on it. And that way everybody's involved. And I was like, that is brilliant. Try it out. It's a great way to end the Netflix debate. But those single nuclei, the reason that's so cool is because like it allows the heart fiber. There's not too many cooks in the kitchen. There's one person, making all the decisions, and those decisions get made and they contract when they need to, right? And then all the fibers are interconnected. So that also helps them all contract together. That's going to be really important because, again, the heart's main job is to generate pressure. And if we're generating pressure, we need things to relax all at once, and we need things to contract all at once because we're trying to create high and low pressure gradients. So cardiac muscle, a little bit different from skeletal muscle. It doesn't have it's striated, but like lightly, it's not as heavily striated as like skeletal muscle. It's got single nuclei instead of multiple nuclei. Your skeletal muscle also has like a lot of nuclei because like the nucleus can sort of turn into more like heart, like more skeletal muscle later. And so we need to be able to grow skeletal muscle a lot better. Having more nucleuses allows that to happen. It is involuntary, whereas your skeletal muscle tends to be very voluntary. We don't have any control over our heart. It is strictly designated to the autonomic part of our nervous system. Now, sometimes I get people who debate me on that, and they're like, I do a lot of yoga and meditation. I know how to control my heart. No, you don't. I hate to be very black and white about this, but I have to be. We do not have any control over how fast our heart beats. However, you can do certain things. You can think, calming thoughts. You can control your breathing. You can do all these things that, yes, that does slow your heart rate down. But if you had conscious control of your heart, you would completely screw up the pressure gradient. And that is something we do not want to have happen. And then one thing that's very unique about cardiac muscle that we do not see in our skeletal muscle is that we have what are called intercalated discs. And intercalated discs are these really cool little discs that are sort of situated between the cells that allow electricity to very quickly run across the entire heart muscle. And that's going to become really important in just a little bit when we look at that electric charge. So as electricity runs across the heart, it's all very in sync and it travels very, 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 very quickly. So that's what's cool about that inner layer, right? It is very similar to our skeletal muscle, but it is just slightly unique. So we got the really smooth inner layer, we got the thick muscular layer, and then we have the outermost layer of the heart called your epicardium. And this is just like the outer layer that, you know, encases the muscle, right? We need to have like a layer that separates the muscle from, you know, anything else. And so we are going to see the epicardium there. And then you are going to see what is called the pericardium. Now, the pericardium peri is perimeter, right? It's around the perimeter of the heart. And that's exactly what it is. It's a fibrous sac that encloses your heart and it holds it in place there. So the pericardium is this big sac that kind of holds everything where it needs to be. Now that seems like it might be part of the heart, but technically it's not actually part of your heart. It's just connective tissue that holds your heart into the center of your chest. I can't remember when I was talking about this, but we were talking about at one point, we were talking about what's called Marfan Syndrome. And Marfan syndrome is a connective tissue disorder where you'll see people will usually be very like long and lanky because their body can just continually kind of keep growing due to having like very little connective tissue. So their connective tissue is a little bit weaker and their joints aren't held together as closely. And so there's some space between their joints, which gives them this appearance of being like extremely long and lanky. So he's like really long hands and stuff, right? So here's the thing, you know, Marfan syndrome seems really great sometimes, but one of the problems with it is that what is causing this big stretching of these of like the bones that allows them to have so much space is because the connective tissue that's supposed to pull our bones together and hold them together is just weaker in Marfan syndrome. So that actually includes the heart, which is why you would think like somebody that tall and that lanky would be really great in like the NBA, where it pays to be very tall, right? But the NBA actually won't let anybody who has Marfan syndrome be in the league. And the reason for that is because their connective tissue is weak enough that it could cause their heart to literally fall out of their chest because the pericardium, which is holding it and, you know, this connective tissue that holds everything in place, literally can become dislodged. And that's not awesome. And then one other really cool thing about the epicardium and the pericardium, because like one is the actual heart itself and one is a sac surrounding the heart, we do not want those layers to get stuck to one another. So there's this mucus layer in between the two that makes it extremely slick. And so the sac never gets stuck to the heart when the heart does its like moving and contracting, right? Now there is like a disease like pericarditis, for instance, which is where you can get an infection in between those layers, and like a little bit of fluid, like a little bit of water, kind of gets between those layers of the heart, right? And so then it gets inflamed, and you can see that sac right there, and that can cause the sac to be less slick. You know, we think water is very slick, but it's definitely not as slick as like mucus, you know, or like it's not, you know, like those things are extremely slick. And so what happens is like it can actually stick to the chambers of the heart and it can keep the heart from contracting. And that's why pericarditis is so dangerous. Very common in people who get like bacterial infections, right? So definitely something we are trying to avoid. So pericardium, like I said, I'm supposed to say this earlier. Like I said, is a fibrous sac that sort of encloses the heart, made up of several different like serous slick layers. So, like I said, it's lightly striated. It has single nucleuses. It is very involuntary. And because of all of that coming together, it is very, 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 very good at contracting all at once, which, if we are trying to generate as much pressure as possible, is a very good thing, right? That's exactly what we want. So, next thing we're looking at are the chambers of the heart. So this is something we do want to get pretty familiar with. When we are looking at the various chambers of the heart, we want to understand where all of the blood is flowing. This is a really great picture. So if we take a look here, we're going to divide the heart into 4 main sections here. Now, I actually kind of like to picture this in my brain as sort of a Valentine's heart. Obviously, our heart looks like this, not like a Valentine's, heart, but it actually is a pretty easy way to kind of divide it if you think about it that way. So if we take like a picture of the heart here, I know there is one. Yep. Kind of like this, right? We can actually divide this pretty easily if we put a couple like sort of dividers here, right? So if we go and just kind of divide the heart down into 2 different sides here, right? And then if we divide it into like a top and a bottom, right? Now we've got sort of 4 quadrants in our heart. So if we call this like the left side of the heart, I'm sorry, we call this the right side of the heart, because remember, this is from the anatomic perspective. So this is going to be the right side of the heart over here. This is going to be the left side of the heart over here. This is going to be the upper portion of the heart here, and this is going to be the lower portion of the heart here. So now we've got 4 quadrants, right? And they're each going to have like sort of a different task, a different role. And you can see that here, right? You can see there's sort of the blue side of the heart over here, and the red side of the heart over here. We'll explain why that makes sense in just a second. So your heart is a double pump. It is not only in charge of like pumping, blood to the lungs, it is also in charge of pumping blood out to the entire body. So when we are looking at the chambers of the heart, the reason we have a red side and a blue side is because the red side is representing oxygenated blood. That is blood that has a lot of air in it so that it can deliver blood throughout the entire body. So that is what is known as the systemic circuit. Systemic because it is traveling to all of the other systems in the body, your brain, your nervous system, your skeletal system, your digestive system, right? It is traveling everywhere. And then you've got your pulmonary circuit, which is going to your lungs, and that's your pulmonary system that we're going to talk about tomorrow, actually. So you've got a systemic circuit and a pulmonary circuit. They both travel in different directions to different places to deliver oxygen or to go pick up oxygen. It's just moving stuff around to wherever it needs to go. So we go back to our picture here. We're going to kind of change this slightly. And we're going to say that this is the right side of the heart. The right side. And we're going to put this side over here. And that is going to be the red side. That is going to be the left side of the heart, right? So let's go ahead and put some little chambers in there, right? So for the left side, we'll put like a chamber up here, right? And we'll put another chamber over here in the blue side, right? So these chambers, right, are representing where blood is going to go. Now, this upper side part of the heart, right? This upper portion of the heart is responsible for gathering blood, right? So this upper chambers let me redo my chart. These upper chambers, right, are responsible for gathering blood, right? So these gather blood. That's their main job, right? Is to gather blood. Now, the right side is gathering deoxygenated blood, and the left side is gathering oxygenated blood. The lower chambers are also responsible for their job. Their job is the lower chambers are responsible for pumping blood. So that's where the real heavy lifting of contraction takes place, right? So they're in charge of pumping blood around. So we got gathering blood up top and we've got pumping blood down below. And that's where we get our different chambers here, right? So we're going to put a big old chamber. We'll put a big old chamber here, right? And then we'll put a blue one down here. Right. So there's our various different chambers of the heart. So the upper chambers, again, are gathering blood, and then the lower chambers are sort of pumping blood away, right? So if we look at how this works, right, this is sort of like a double figure eight, right? Blood goes into the heart and gets pumped out either to the body or to the lungs. So let's go ahead and track like one singular red blood cell. So that blood cell is going to go from heart to lungs to heart to body. Again, sort of as a double figure eight here, right? Heart to lungs to heart to body to heart to lungs to heart to body. So that's the double pump that we're sort of describing here. So the right side, which is this this blue side here, right? The right side is going to pump deoxygenated blood or low oxygen blood over to the lungs. Okay, that's your pulmonary circuit. So what's going to happen in our little Valentine's Day heart, right, is that blood's going to come into this chamber right here, and then it's going to continue down into this chamber here. Okay, so the upper chamber gathers that blood, and it gathers it up with a bunch of other red blood cells so that it can pick up enough red blood cells to generate enough pressure that when we finally open up the valve, down here, what's going to happen is it's going to go rushing into this chamber here. And then those valves are going to slam shut. And so now more and more and more pressure is going to build up in here. And then eventually that's going to pump it out, and it's going to travel out of the heart, and it's going to kind of split here. Some of it's going to go over to like that lung, and some of it's going to go and split over to that lung, right? So, we need some lungs over here. Like, I'm actually not going to draw lungs, but it's going to go out that way, right? It's going to get pumped out over to the lungs, right? Here, I'll make these arrows just like a little bit bigger, right? So we'll go like this all the way over here, right? And we'll split it and send that one over there. So there we go. Right now we have sort of pumped everything out of there. I'm just going to give myself a little bit more space. I'm dragging this down here. There we go. So that is the systemic side of things, right? The systemic part of our cardiovascular system, right? So again, blood enters this right atrium and goes into the right ventricle, and then gets pumped over to the lungs. Now, we got to get it back from the lungs, because now all of that, all those red blood cells just picked up a whole bunch of oxygen, right? So now they're going to come back in through and go to the systemic circuit. So what's going to happen is blood is going to get into this right atrium right here. Then eventually it's going to travel out to the right, over to the, I said right atrium, sorry. Doing the heart's so complicated because it's backwards. So it's going to go into the left atrium, where now it has a lot of oxygen. It's very oxygen rich. It's going to go into the left ventricle there, and then that is going to pump it to the various parts of the body. Some of it's going to go up to the brain. Some of it's going to travel down throughout the entire body, right? And so that is going to send blood to where it is going, right? So hopefully we get to kind of see that happening in real time. Here's a much cleaner picture, right? So it goes into the left atrium, into the left ventricle, and then out to the various parts of the body, right? Some of it's going to go up to the brain. Some's going to loop down behind and travel out to the various parts of the body. So those are the two sides, right? We've got the pulmonary circuit and the systemic circuit. The pulmonary circuit pumps it out. Now, when you're memorizing this stuff and you're looking at these 4 chambers here, you kind of want to, honestly, the way I do it is I picture like this little quadrant, right? I've got a right side and I've got a left side, and I've got an upper and I've got a lower. So the upper portion of the heart, those are the chambers that are, both of those are your atriums. You've got a left atrium and a right atrium. Okay, so the left atrium is responsible for gathering blood that returns from the lungs, right? That left side of the heart is pumping blood throughout the body, right? And then the right side of the heart is gathering it, that's like coming back from the body, right? So the right atrium receives blood from the body. This is low oxygen blood, right? So honestly, let's look at it from like the perspective of a brand new red blood cell, right? Let's say your femur, makes a brand new red blood cell, and it's going to enter the body for the very first time in its short little life cycle, right? So a brand spanking new red blood cell enters the bloodstream. It's never picked up oxygen before. It's never carried carbon dioxide or, deoxygenated before. It's never done anything. So what it has to do is it has to get over to the heart for the very first time. So it travels through the systemic circuit. So it's sort of released into the systemic circuit there. And then eventually makes its way to the heart for the very, very, very first time. So what it's going to do is that new little red blood cell is going to get sucked up into that right atrium. It's a low oxygen blood cell, right? It's never carried anything before. So it goes into the right atrium, and then it gets pumped into the right ventricle, because as the right atrium sort of fills up with more and more red blood cells, the pressure increases, but this valve is closed. So it's filling and filling and filling and filling, right? And then there's like a lot of pressure. So what ends up happening is this valve opens up, right? And then all that blood goes rushing into the right ventricle. And then as it starts to fill up, the valve closes down again, right? And so the valve goes and closes back down. Our new red blood cells hanging out in here. Now the heart's going to contract. That's going to create like a very intense lack of space here. And so now all those blood cells are looking for some place to go. Can they go back to the right atrium? No, this valve is closed. But this valve right here opens up. So that red blood cell gets pumped out over to the lungs. And for the very first time, our new little red blood cell picks up oxygen, right? So now it's got a ton of oxygen in itself, and it's ready to deliver it to our glute muscles or our calf muscles or our biceps or triceps, or maybe it's going to the digestive system or the brain or something, right? It's got to go deliver that oxygen. So now, right, the left atrium is going to open up, and that creates all this space, and there's all this pressure in the lungs, right? So there's all this empty space over here, and there's like a lack of space over here. So what happens? All the red blood cells, including our new little red blood cell here, our little rookie red blood cell, enters into the left atrium for the very first time. This valve is closed, so pressure is building, and then all of a sudden the valve opens up, goes rushing into the left ventricle. The valve slams shut behind it. So then the heart starts squeezing. There's a severe lack of space. Can it go back to the left atrium? No, it cannot. So it travels up this valve, and maybe it goes up to the brain, or maybe it loops around behind and goes out throughout the rest of the body, right? But now, let's say it goes up to the brain, right? It travels up there, delivers oxygen to the brain, and the brain is going to exchange that oxygen for carbon dioxide, CO2, right? So now it is a deoxygenated, we'll say blue red blood cell. It's not actually blue, but we'll say it is, right? It's deoxygenated. So what does it need to do? Well, for the very first time, it needs to drop off its CO2. So it travels back to the right atrium, to the right ventricle, over to the lungs. It becomes oxygenated again. Left atrium, left ventricle, up to the brain, rinse and repeat. Heart to lungs to heart to body to heart to lungs to heart to body to heart to lungs to heart to body, right? So there's our sort of double figure eight there, right? So easiest way to memorize this stuff, guys, if you want to keep the chambers of the heart memorized in your brain, easiest way to do it is to work your way backwards, okay? In my opinion, easiest way to remember this is to remember this ventricle right here, the left ventricle, okay? So ventricles are in charge of pumping blood out to the body, Okay, that's what a ventricle does. So both of your ventricles, right, are in charge of like pumping blood out of the heart. The left ventricle pumps it everywhere throughout the body. The right ventricle pumps it over to the lungs. So when you look at the heart here, you'll notice, look at this like right side. You can see it's kind of got, that's got some heart muscle here. It's got some heart muscle here, right? But look at this side over here. This is like a little bit thicker. There's a lot over here, right? The left side of the heart is much, much more muscular than the right side of the heart. You can kind of see that a little bit better in this picture here, right? Look at how thin this wall is over here, right? They both share this thick wall here. And then this is all really, really thick, right? That's because the left ventricle has to pump blood over greater distances. So like when you are feeling your pulse, right? You place it on your wrist, you place it over here, right? What you're feeling is the left ventricle squeezing, and it creates like some pressure that runs throughout the entire body. Your pulse is whenever your left ventricle shoves more blood into the tubes. And so they stretch for just a second and we can kind of feel that outside, right? So the left ventricle squeezing, right? And sending blood to your brain, to your digestive system, to your muscles, it's going everywhere. So that's the one I always tell people to memorize, because now, if you remember that the left ventricle is the chamber of the heart responsible for ejecting blood throughout the entire body, well, now you can go, okay, well, the opposite of the left ventricle would be the right ventricle, right? And if the left ventricle sends it to the body, then the right ventricle would send it to the lungs, right? Those are opposite places. So there we go. Now I've got my oxygenated blood that's going throughout the body, and I've got my deoxygenated blood going to the lungs. So you memorize it this way, and you got your sort of opposites there, right? And so there's your lower quadrants memorized, right? The lower chambers pump blood. The upper chambers are going to gather blood, but this chamber pumped it to the body, and this chamber pumped it out to the lungs. So the right side goes to the lungs, and the left side goes to the body. And now our sort of like 4-quadrant chart is sort of complete, right? We've got these different chambers going to different spots. So if you remember the left ventricle, you'll remember that it is going to go throughout your entire body. You are feeling the left ventricle when you feel your pulse. Right ventricle goes to the lungs. Now, where do both of the ventricles get their blood from? Well, they're delivered from their respective atria. So left ventricle is attached to the left atrium, right ventricle is attached to the right atrium. So when blood travels here, the left atrium's receiving blood from the lungs, and the right atrium's receiving blood from the body. So you can sort of work your way backwards as long as you have one of those chambers memorized. Memorize that left ventricle, guys, and it will help you remember all 4 chambers of the heart, because all you have to do is sort of work your way backwards, So left ventricle pumps blood throughout the entire body. It's attached to the left atrium, which is getting blood from the lungs, because if it's going to send blood throughout the body, it's going to be oxygenated, right? And then the right ventricle is getting blood towards the lungs, which means it must have just received low oxygenated blood from the right atrium. So I know it's kind of a lot to kind of memorize. That stuff's kind of a pain in the butt. The chambers can be kind of difficult sometimes, but hopefully that kind of helps, right? Again, looking at a new red blood cell, it would go from right atrium, right ventricle, lungs, left atrium, left ventricle, body, back to the right atrium, right ventricle, lungs, right? Again, it's just a big figure 8. Any questions on that? Is that pretty clear to everybody? We're getting those chambers kind of taken care of there?
Yeah, it's just a cycle. I think it's just like it comes in through one side, it cycles in, and then it goes in throughout the other, and it just like it serves just a purpose.
Yeah.
So it's like it comes in through, like, for whatever reason it comes in, and then it needs to come out for that reason. So
we do know the reason. Remember, the reason is because of space, right? So it's a
yeah, that's
right?
what I mean. But like for the specific reason, right? Like you're your heart would pump reason. I mean, your heart would pump blood for what it needs to, is what I'm trying to say.
Sure. So the left side is going to pump it throughout the body because it needs the oxygen, and the right side is going to pump it to the lungs because it's dropping off CO2. Yeah, that's a good way to reason it.
Okay.
All right, so let's go ahead and take a look at the heart itself. By the way, all of that like moving is thanks to our valves, right? Those valves either closing or opening are going to create these areas of high pressure. This is one of the reasons why we do not want to experience muscle growth in our heart. So like you might think like bigger muscles, that's awesome, right? We like bigger muscles. We do not in the heart. We do not want more muscle in the heart. Weirdly enough, we want a stronger heart, but we don't want it to get any bigger. When your heart actually gets bigger, that can pull those like little valves apart, right? They're supposed to like, kind of flap down and kind of close like this. But if you pull them apart, right now, there's sort of a gap there and your heart can start leaking. And that's definitely not something we don't want blood to backflow. We want it to travel in the direction that it's going. So that's one of the reasons why it's so important to get an even amount of blood flow to the heart itself. Now that seems kind of weird. You would think like, oh, well, there's so much blood in the heart, right? Like it's gathering all the blood in these chambers. You would think it would just kind of get its oxygen there, right? But that's not quite how it works. Like we actually don't extract oxygen passively from the chambers of the heart. Instead, your heart is just like any other tissue running throughout your body. It is covered in blood vessels, right? So when we look at like, what is called like a capillary bed, and we're going to see that in a little bit. A capillary bed basically covers tissues to ensure that like those tissues are getting oxygen, right? Like your lungs are covered in these little capillary beds, right? Your tissues are covered in these little capillary beds. Well, your heart is actually covered just like that, but in really big tubes, because this is something that needs a lot of oxygen. So whenever we want to like give a tissue blood and deliver nutrients and deliver oxygen, or maybe pick up waste products, right? Whenever we need to do that, we have a series of like arteries or, blood vessels that are going to cover it. So these are what are known as your coronary arteries. Your coronary arteries are the first place blood goes as it leaves the heart. So this is the very first spot. When you look at your aorta, which is that sort of main chamber, main tube that travels out of the left ventricle. Remember, the left ventricle pumps blood throughout the entire body, right? So the first place it's going to go, the big tube that it travels out, that either goes up to the brain or circles around and goes out to the body, it has these little tubes that branch directly off of it. The very first place that blood goes in the heart is the heart itself. So it circles out of here and then comes down and supplies the heart itself with blood. Those are your coronary arteries. So like, when you're on a plane and they say, if oxygen masks should drop from the ceiling, secure your own mask before helping someone else, right? The reason you do that is because you can't help anybody if you pass out, right? You'll be able to actually help more people by making sure that you are safe first. Your heart takes the exact same sort of like structure, right? It supplies itself with blood before anything else. So we definitely want to make sure we do not screw up any of those vessels that are going directly to the heart. We want to make sure that blood can travel through those vessels very, very easily, because let's say plaque or blood clots or something starts building up, maybe we have like a really bad diet, maybe we don't exercise regularly. And so then passive blood just starts building up on those blood vessels. It's going to limit blood flow. And if we limit blood flow to the heart itself, right? Well, now this is the thing that's responsible for pumping blood to everything else. So if this pump here cannot pump blood effectively due to the fact that like it's not getting enough oxygen, well, that is what we literally call a heart attack. It comes from what is called coronary heart disease. It's the buildup of plaque on the inside of these arteries right here. These arteries are responsible for giving the heart its own blood. And so when it does that, it gets decreased oxygen. Decreased oxygen causes its cells to not be able to function. If its cells can't function, guess what? The heart can function. If the heart can't function, nothing else in the body can function. So that is sort of what we talk about when we talk about like coronary artery disease or coronary heart disease. It's what leads to heart attacks. So this is sort of what those valves look like, by the way. Don't worry too much about this, but like, you know, it's going to open up to allow blood flow, and then it's going to close down to sort of stop blood flow. So whenever we're looking at our cardiac cycle here, whenever we're looking at these contractions of the heart, we are talking about like our heart beating, right? So there's going to be sort of two versions of a cardiac cycle. We are going to have what is known as systole, and we are going to be known as what is known as diastole, right? So you have a systolic contraction of the heart, and you have a diastolic contraction of the heart, and it looks something kind of like this, right? So you can see the bottom of the heart squeezes blood out of the heart. The upper part of the heart sort of opens up to receive that blood, and when it squeezes, when the top squeezes, it just sends blood down into the lower chambers there. Actually, I could slow this down a little bit. There we go. See how it squeezes from the top and then squeezes from the bottom, right? So the squeezing the top fills this chamber down here. Squeezing from the bottom pumps blood out of the heart. So systole is the actual heartbeat that's pumping blood out of the body. That's your systolic blood pressure. It's very active, right? Systole is the contraction of the heart. Diastole is sort of the passive relaxation of the heart. So when your heart squeezes, that is systole, and when it relaxes, that is diastole, okay? So systole is the top number when you are looking at your blood pressure. Right, when you are looking at blood pressure, we always write it as, let me try systolic versus diastolic. You know, we always write it as like 120 over 80, right? That is the systolic number up top. That's the 120. The diastolic number down below, that is the 80, right? So the reason we like those numbers is because that's the average amount of pressure that is going to effectively deliver blood throughout the body without ever worrying about blood pooling in one spot. If your blood pressure is too low, it's not going to be able to travel. I mean, you know, imagine like blood pressure is too low, tries to get up, but then gravity just kind of like falls it back, right? That's not going to be very good, right? If your heart's really weak, that's not going to work very well. Or if pressure is too high, it'll create areas of high pressure in one spot and areas of low pressure in another. So then blood just ends up rushing to the area of lowest pressure, so it can just kind of stay there, and then it doesn't move, right? And that's why high blood pressure is so bad for us. It means that we can't deliver blood where we need to go. So we have our systolic blood pressure up above, and we have our diastolic blood pressure down below. So ideally, we want our blood pressure to be around 120 when the heart is squeezing, right? Obviously, when it's squeezing, there's higher amount of pressure. And we want it, when it relaxes, to be somewhere around 80. If it is anywhere over 130 over 90, I'm sorry, 140 over 90, that is what's known as hypertension. So 140 over 90 is considered high blood pressure, and that can be very dangerous because when you have high blood pressure, you're basically just having pressure problems. You cannot get blood to travel where it needs to go properly. And so like that's going to mean that certain tissues are not getting blood. Right. So the entire cardiac cycle is your diastole, which is the opening up of the heart, allowing blood to sort of fill everything up. And then systole is where the heart actually contracts to sort of pump that blood all around the body. So we want to be able to measure this function, right? As trainers, it's really important for us to be able to measure how well our client's heart is functioning, because like the cardiovascular system is one of the biggest things that we train, right? We do a lot of cardio. Even strength training counts as cardio, right? Last night, we were doing some strength training, and hopefully everybody was, or yesterday, you guys were feeling that elevated heart rate, right? Like all those lunges, all those squats are going to kind of get your heart rate up. So when we look at that, the overall function of the heart, we're going to call that your cardiac output, because like it's the product of how well your cardiac muscle is contracting and how much blood is moving throughout the body, right? So cardiac output, we're gonna write that as Q in our little equation here, right? Because it's the quotient of blood that your heart is sending out. So cardiac output is the overall function of the heart. It is the measurement of how much blood can be pumped out of the heart per minute, right? And so it's going to be made up of two things. It's going to be made up of your stroke volume, which is the amount of blood pumped per beat, right? And your heart rate, which is the number of beats per minute. Now, obviously, like this is really valuable information for us as trainers, but we can't really measure the stroke volume of our client, right? Like I don't have a machine that's going to allow me to measure how much blood's shooting out of their heart every time it beats. But remember, the cardiac output is two things that come together. It's that stroke volume, which is the amount of blood every time it beats, and heart rate, which is the number of times that it beats. So follow me on this, right? Let's just say I need to move 1,000 pounds worth of weight from point A to point B. So I got to get 1,000 pounds of little 5-pound plates, right? I got to get 200 plates from over there to over there, right? Wait. Yeah. So I've got 200 little 5-pound plates. I need to get them over there, right? If I can only carry 2 plates at a time, right? I'm only carrying like 10 pounds every single time. That is going to take me a lot of trips, right? I'm going to have to move back and forth. And if you give me 20 minutes to get this done, right, I'm going to be running back and forth as fast as I can, right? And so I'm going to be traveling at a pretty fast rate because I can't carry very much weight every single time. But let's say I can carry 10 plates at a time. That's going to be 50 pounds every time, right? It's not going to take me very many trips, and I can go a little bit more slowly, right? But I'm carrying so much more weight every time. I get the job done in less trips. That's exactly how your heart rate works and your stroke volume, right? Your stroke volume is how much blood moves every time your heart beats. And your heart rate is how often it beats. So if your heart can pump a lot of blood all at once, it can beat less often. And this is one of the reasons why we use heart rate as like one of the measurements of overall fitness with our clients. The lower your resting heart rate is, the more efficient your heart is working. So it can beat less often because your heart is very strong, right? So if I were in a race with Dion, the two of us both run exactly 1 mile, and we both run it at like, let's say 7 miles per hour. So that's a 7.0 on the treadmill, right? And we both do exactly 1 mile. And at the end of the race, right, Dion's heart rate is like 140 beats. And at the end of the race, my heart rate is like 160 beats, right? That shows that his cardiovascular system is in better shape than mine, because we were both able to travel the same distance and the same length of time, but he was able to do it with less heartbeats. I had to beat more often because I was pumping less blood every time. And so I have a less efficient heart. This is one of the reasons why we train our clients' heart rate, and we celebrate when their heart rate gets lower and lower and lower as they get fitter and fitter and fitter, right? So your cardiac output is your heart rate, the number of times you have to beat, versus your stroke volume. If your stroke volume, so we have oh, wait. Equal, that's Q. Equals, that's rate, that's HR. times stroke SV. So there's our little equation, right? Cardiac output equals heart rate times stroke volume. If my heart rate was, let's say, 130, and my stroke volume was only, let's say, 10 units of blood, right? My overall cardiac output is going to be 1,300, right? But let's just say I move up that stroke volume a little bit, and now I'm pumping like 20 units of blood, but I need a cardiac output of 1,300. Well, now my heart rate is only going to be 65 beats per minute, right? That is a substantial difference. And let's say, like, I bring my heart rate up to 130, the same way that we had it before, right? And so like now with a stroke volume of 20, I'm bringing my heart rate all the way up to like 130 beats per minute. I'm probably covering some serious distance now, and I'm a super athlete who's pumping 2,600 units of blood. I can probably travel pretty freaking fast, right? And pretty freaking efficiently. So it doesn't matter like what number you move around, but that's what we're paying attention to. We measure heart rate because we know it is related to the overall performance of our heart. Does that make sense to everybody? Questions on that?
Yeah, that makes sense. So it's like the more your heart struggles to pump blood, the more out of shape you are, right? In a sense.
Yeah, pretty much. It's a direct, it is a direct thing that we can, sort of analyze and pay attention to. This is why we have like what's called, so Cyrus stating, we're going to teach this pretty soon here. This is why we have what's called the YMCA step test.
Oh, the mile where you walk a mile? Oh no,
that's
not
the Rockport.
The Rockport.
Yeah, we use both those, right? Rockport walk test is how fast can you walk a mile? What's your heart rate at the end of that mile, right? And so that's a really good way to test how good a shape you're in. We also use what's called the YMCA step test. And it's where everybody steps on a step for 3 straight minutes uninterrupted. And then we measure what their heart rate recovers to after a full 60 seconds. So the Rockport walk test is kind of about like your performance over a mile. The step test is really much more about like how fast your heart recovers. Both of those things are related to like how good a shape we're in, right? So if I'm 33 years old, right? And I do 3 minutes on the step, and then I turn around and sit, and my trainer tests my heart rate over like a full minute. It's like bum, 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 bum. And it recovers, right? Like I'm not doing any more work. I'm sitting there, right? And so my heart rate's really fast in the beginning, kind of slows down at the end, right? And my heart rate recovers to, let's say, 119 beats, right? Well, that's going to put me somewhere between 114 and 121. At 33 years old, that shows me that I'm not in very good shape. That shows that like I really do kind of need to train my cardiovascular system a little bit better. So my trainer works with me. I do some cardio, and 6 weeks later we retest. I do the same number of steps. I do the same length of time. I sit on the step, and my heart, again, it's traveling fast. And then it starts to kind of slow down, right? And then eventually my heart rate's all the way down to, let's say, 100 beats per minute, right? So now I'm somewhere between 96 and 102. Now I'm in average shape for somebody of my age, right? It drops even further. I'm above average, even further than that, until eventually I get into really, really, really good cardiovascular shape. And so that's how the sort of, that's sort of how the sort of pace is actually working. Oh Lord. Sorry guys, 1 second here. Apparently, I'll text Alyssa really quick. She's having some trouble. So that is sort of the overall function of our heart and how it actually, works and stuff, right? So now we got to take a look really quickly at some of the physiology of our heart and how it actually does all of this, right? So if we're looking at our heart, our heart is made up of we call it a conduction system. It's very good at conducting electricity because it is very good at producing electricity, right? So when you look at your heart, and again, it's under the control of your nervous system. That's either going to speed it up or slow it down. Your heart is going to generate electricity the same way that everything else does, right? Go back to what we were talking about the other day when we talked about action potentials, right? It's where your body sort of pumps sodium and potassium from one place to another, right? This can happen in a muscle cell and it can happen in neurons, right? We flush sodium and potassium from one spot to another, and it sort of causes it to travel, well, continuously down, in another direction, right? This little positive charge continues traveling down wherever it needs to go. If that's rushing over heart cells, that's going to cause the heart cells to contract, just like it would in like a skeletal muscle cell. So all of this needs to be under the control of a central system in order to control the rate at which your heart is beating, because again, your nervous system is autonomically doing this. So when you have like a lot of lactic acid in your blood, it will actually cause your heart to increase its rate. Like if I were to take like a syringe of just pure lactic acid and inject it in, right? What would happen is like my heart would actually start beating faster in response because my body would go, oh man, we must be working out right now. Like there's all this lactic acid buildup, right? So the central node that's getting all that information from the brain is called your cyanoatrial node. It's this little node right here. It actually lives in your right atrium. And so there's our cyanoatrial node. It initiates the signal that it's getting from the brain, which is why we call it the pacemaker of the heart. This is the part of the heart that is responsible for telling your heart how fast to beat. So if your blood returns to a normal level, it's not very acidic anymore, then the cyanoatrial node will send signals throughout the rest of the heart saying, hey, we're good, let's go ahead and relax, right? So this is the pacemaker of the heart. It's a special node that actually regulates your heart's rhythm, right? It lives in your right atrium, and it is under the control of your autonomic nervous system, right? So it'll start here, and then that signal will rush across the top of the heart first, and then eventually it'll travel down here to this little node. This is called your AV node. It actually delays the signal, weirdly enough. That sounds kind of weird because you're like, didn't we just talk about traveling as fast as we can with this signal? But the reason for that is because if we delay the node, this will finish, the upper part of the heart will finish contracting, and then the second lower part of the heart can contract afterwards. And that's one of the reasons why we sort of see your heart actually beats top to bottom. And it kind of goes like bump, bump, 1, 2, 3, 4, and so the heart will finish up top before it gets down below. And that is actually allowing us to create, again, an area of high pressure, which pushes the blood down here. And then we create this in an area of high pressure, which pumps it out of the body, out to the body, to the lungs or everywhere, right? So that's your cyanoatrial node. Now, like I said, this is under the control of your autonomic nervous system. You do not have direct control of all of this. So although your SA node is setting the pace, your nervous system is in charge of telling it how to do that. So like if you flush your you flush your body with, epinephrine, which is adrenaline, or thyroxine, right? Those two hormones tell your SA node to start beating faster, right? If you pump it full of lactic acid, it'll beat faster. And if you pump it full of like, dopamine or, serotonin, that will cause it to kind of slow down because it's in a rest and digest situation, right? So that is sort of how that's all going to work. So there's your brain, the parasympathetic part of your nervous system, sort of interacting with all of these various nodes here, telling what chambers to speed up and what chambers to sort of slow down. So obviously, like, we do have a lot of diseases associated with the heart. And so like, we need to be able to treat those diseases. And some of the best way to do it is to train the heart, right? When you exercise, not only are you strengthening the heart's fibers by, making them work and experiencing strength and cellular changes, just like we adapt to exercise in the rest of our body, right? Not only are you doing that, but you're also increasing your body's nervous system response to stress, right? You're speeding it up, you're slowing it down, you're doing everything you need to do to get it to calm down, to get it to work, depending on what situation you're in. So then your body learns, oh, well, work's not that bad. This is very good for me, and it's like, oh, I'm in a stressful situation, but I always overcome my stressful situations, right? Now, obviously, like certain, medications can affect that as well. Best thing to do with like somebody who has had a heart attack is to get them to, change their lifestyle, exercise regularly, work on their diet. But there are obviously like different medications out there. There's anticoagulants, there's statins, all these things that like have, some type of effect. Heart surgery itself, there's all kinds of different things you can do. You can put a pacemaker in. That pacemaker is basically working as your cyanoatrial node. So they'll usually put it sort of just like right there under the skin a lot of times, or sometimes they'll do one that kind of hangs out. Actually, they'll have like what's called a fissure, a little hole. But that basically threads directly into the heart and, allows it to, whenever that freaking SA node doesn't do its job, the pacemaker, zaps the heart for it, right? Sometimes they'll do like a coronary bypass. If you have like a lack of blood flow, they'll, move like a different artery over there to allow that to happen. Sometimes they'll need to like clear out the plaque. So what they'll do is they'll fill it with like a little balloon here. And then that pushes all the plaque away and opens up the vessel again. If they need to, a lot of times they'll put a stent in, and a stent is like this little framework that kind of clicks open and it stays open forever after that. So they'll thread it in with they'll send the balloon in that pushes all the plaque away. They'll send another balloon in, and then they inflate that balloon and it clicks the stent open. And then you got to go in for regular checkups to make sure your stent doesn't slide out of place. But those are some of the different like heart surgeries and sort of, how those work. So last little bit we're going to look at today is we are going to look at blood pressure. So as we are looking at blood pressure, we got to talk about our blood vessels, right? Because they are sort of what's regulating some of those pressure changes, right? Like your heart's in charge of like sending the blood around, but the vessels, if they dilate, is going to increase the pressure, and if they dilate, I went like this, dilate, that's going to decrease the pressure, right? And when they constrict, that's going to increase the pressure. So now that's great because we can create areas of high pressure where we don't want blood to be, and we can create areas of low pressure where we do want blood to be. So when you start exercising, for instance, right, I want to shut down blood to my digestive system because I'm not using it right now. I'm trying to lift weights, right? As I exercise, right, my skeletal muscle will increase or dilate my blood vessels so that blood will rush to those areas, right? Same thing, or if you're cold, right? If you're really cold, your blood vessels will constrict near the skin so that they don't continue picking up that cold temperature. And if you're hot, they'll dilate because they're trying to get rid of that hot temperature. So this is a closed series of tubes. Now, this is where some more memorization and vocabulary comes in. We worked on the chambers of the heart earlier. Well, now we got to kind of memorize which blood vessels are which, right? So you're going to have 4 types of blood vessels, right? Well, that's not entirely. You're going to have, 3 types of blood vessels. That's an easier way to think about it. So you got 3 types of blood vessels here. You've got arteries, which are blood vessels that are carrying blood away from the heart, okay? So arteries always travel away from the heart, no matter what, right? Now you will have, like, if we look at the picture here, a couple blue arteries, although there's only a couple of them. And most of the arteries throughout the body are red because we are traveling, there's just more body than there is straight to the lungs, So whenever we're pumping blood out of the heart and it's traveling away from the heart, that's traveling through an artery. So here's your pulmonary arteries going over to the lungs, right? And those are the only real blue arteries we've got. And then we got our systemic arteries going literally everywhere else. So some up to the brain, some over to the arms, right? Some of it travels down to the digestive system and like organs and stuff. And then some travels to like the legs, going all over the place, right? So if it's going away from the heart, it's an artery. Now it will branch like smaller and smaller and smaller, And eventually it'll sort of branch off tinier and tinier until we call it an arteriole. An arteriole is just a very small branch of an artery. And eventually it gets so small that it becomes a capillary. And a capillary will form these little capillary beds that sort of cover tissues. Capillaries are where the actual exchange happens. And you've seen, let's see here, you've seen capillaries before. Now, for the most part, they're microscopic, but if you've ever seen like a bruise, right? What this is you got smacked, right? And then all of a sudden, you broke the walls of the capillary, so blood started leaking out. And now it's just kind of pooling under the skin, and we can kind of see it on the outside there. And that's sort of what a bruise actually is, right? It's just blood sort of like leaking out underneath the skin. A capillary bed is very, 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 very tiny, and it absolutely covers our tissues, right? Some of those tissues are going to be, you know, muscle and organs and glands and things like that. And then some of that tissue is found in your lungs. You know, you'll see them cover these little sacs here that we're going to talk about tomorrow, right? So look at all these like little beds here that are absolutely covering things. Now, are capillaries red, you know, meaning that they have a lot of oxygen in them, or are they blue, meaning that they picked up a bunch of carbon dioxide because they dropped off their oxygen? Well, a little bit of both, right? If you look at you can see some of the capillaries are red, and some of them we draw them in purple sometimes, you know? And that's sort of representing the fact that like this is where the exchange actually happens, right? It drops off the oxygen and picks up the CO2 if it's at the body. The exact opposite happens at the lungs, right? If it's at the lungs, it's going to drop off CO2 and pick up oxygen, you know, and that's why we have to sort of flip the color scheme here when we're talking about, you know, traveling to and from the lungs. But for the most part, we're talking about traveling around the body, you know. So arteries are traveling away. They branch smaller and smaller and smaller until eventually they become a capillary. Now, we need to pick up that blood as well. And that's where veins and venules come in. So veins are blood vessels that travel back towards the heart. Right? So we pick up the deoxygenated blood from the body, or maybe we pick up oxygenated blood if we're at the lungs. But either way, we got to get back to the heart so we can get pumped around to wherever we're going, right? So veins are traveling towards the heart. Venules are the small ones. Venules are small branches that are formed when your capillaries are coming together. So you can see like, you know, an artery became an arteriole and eventually became a capillary. And then a bunch of capillaries started coming together and that became a venule. And then a bunch of venules came together and now we've got like a full-sized vein, and that's going to travel all the way back to the heart itself, right? So venules are smaller branches. Now it's really cool. If you look at the artery, look at like this like muscle that it has, right? Arteries are muscular. That allows them to dilate and constrict really well, right? They can sort of spin open and spin closed, kind of like that. Veins, they have a little bit of the same thing, but not so much. Like take a look right here. Look at how thick the artery is versus the vein, right? Now the amount of space in the tube is actually pretty similar, you know, but the wall is much, much thicker. That is because like there's a lot more pressure in an artery. Because remember, this is when your heart squeezes, right? So blood goes rushing out of there. We need this to be much more resistant to damage. We need it to be a little thicker, right? Whereas veins, like the pressure is really low. We don't want them to be thick because we want blood to have no resistance getting back to the heart. Because think about it. It's got to get all the way from our toes up to our freaking heart. It's got to work against gravity, which is tough, right? So not only do we rely on the fact that our veins are a little thinner, we also rely on the fact that your veins have these little valves in them that your arteries don't have. And that valve prevents like blood from backflowing. So when you look at like your pulmonary vein, or you look at your veins there, right? You know, this is preventing blood from backflowing whenever it travels up. So ideally, it'll travel up, the valve will close, and it'll shut down. This is what a varicose vein is, if you've ever seen that get stretched out. So like, let's say the valve gets pulled apart and it can no longer prevent blood from backflowing. So then what ends up happening is it actually sort of overstretches the vein and sort of screws up the anatomy there. Like if we pull that, valve too far apart and it just gets open, right? That is going to allow it to sort of backflow, and you end up with these varicose veins here, right? Where blood is sort of pooling. And now that's, causing blood to pool, and it's screwing up our oxygen delivery, right? And causes a lot of metabolic problems. Can be very, very painful too. Like I said, the pressure is really low at that point, right? It's kind of like, throwing a ball, right? It travels really quickly at first and it slows down, slows down, slows down. So how do we get that blood all the way back to the heart? Thanks to the veins, thanks to the thin walls. But also, it's cool. A lot of your veins are situated really close to muscles. For instance, the veins in your calves actually run straight between the two sides of your calf muscles. So when your calf squeezes, it actually pushes blood back towards your heart. This is why in the military, and all my vets in here will, you've, I'm sure, experienced this at one point, but they tell you not to lock your knees when you're standing at attention, right? When you're standing in one spot, if you lock your knees, you don't end up needing to use any muscle. So then you don't squeeze your calves, right? So then blood starts pooling in your legs and it doesn't get to your heart, your brain, and your brain goes, I need some blood. Why don't we lay down? And somebody passes out. That is because blood travels this way much easier than it travels this way, right? And it's sort of a protective mechanism. So arteries go away from the heart, veins go towards the heart, and capillaries are where nutrient exchange is going to happen there in the middle. So there are some really big arteries. There's your aorta, for instance. That's the largest one. That loop that kind of travels, that's the very first part, right? It's kind of about the size of a garden hose, actually. It loops up. Some of the branches go up towards the brain. There's some more arteries going up this way, and some of them branch, drops down behind the heart, traveling out to the rest of the body. So you can kind of see that here, right? This is going to go and then loop up and travel down below, pick up a little bit of momentum, kind of like a roller coaster, and then travel out to wherever it needs to go. The exact opposite is true. There's your arteries of the veins, right? You can see here, they're all traveling back towards the heart, so they can kind of pick that up. So you are absolutely covered in arteries and absolutely covered in veins. When we were talking about our little red blood cell that got born earlier, right? You traveled through veins to get to the heart for the very first time, got pumped out an artery over to the lungs, got sucked back into a vein to get back to the heart, and then got pumped out of the heart to go deliver its oxygen to, wherever he was going. So that is sort of how this is happening. Now, when we talk about the exchange, why is oxygen moving from here over to there? Like, why the heck do the O2 molecules move? Well, that's an example of diffusion, right? So this is the other gradient that we talked about, right? Pressure gradients are what allows the blood to move around. Concentration gradients are what allow the chemicals to move from one place to another. So why does glucose go from one spot to another? We looked at insulin, right? Insulin drives glucose out of your blood. Well, it's because it tells your body, hey, there's a lot of sugar over here and very little sugar over there. So then like your body's like, oh, gross. And it pushes all the sugar this way, right? That's what insulin does. Glucagon, exactly the opposite, right? How does oxygen, how do O2 molecules move from like the atmosphere when they're in our lungs into our red blood cells? Well, your red blood cell doesn't have very much oxygen. So it's naturally attracted to go that way. Why does CO2 leave the red blood cell? Well, there's not very much CO2 in the atmosphere. So it wants to move that way. Again, these are concentration gradients instead of pressure gradients. But either way, it's one of the most important, ways that to understand how all this stuff works. If you want to understand like why stuff moves the way it does, a lot of times it's just a gradient problem, Capillary exchange is describing how nutrients, oxygen, glucose, vitamin A, whatever, moves between like the cell, the red blood cell, and whatever tissue it's working with. And it does this through diffusion, right? Where something moves from an area of high pressure to an area of low pressure. And it helps that there's a lot of fluid in the area that actually makes it easier to diffuse something, a little bit of osmosis there. So like if you're at a capillary, blood pressure is going to drive some of that out, and then like water pressure is going to drive it back in, right? So oxygen goes out, CO2 comes in. Questions on that, everybody? How y'all feeling? Cyrus, Danny, checking in with you. You guys are the new folks. How you feeling? Dion?
Good. I'm good.
I'm good.
I'm always trying to keep up with like the unmute thing, and there's like a little, there's like the delay. So I'm always like, who's got what? Feeling good? Love it. All righty. So let's go ahead and lastly just talk a little bit about like this blood pressure that we talked about earlier, right? We said 120/80 is ideal. So obviously all of that is generated by your actual blood vessels. So we have what's called vasodilation, where a blood vessel dilates, and we have vasoconstriction, which is where it actually sort of constricts down. Fun fact, little like the easiest way to kind of remember vasodilation and constriction, originally Viagra was meant to be a pill that was used to help with the heart. That was its original function. It was like, oh, somebody's got like blood pressure problems. It's probably because their blood vessels aren't dilating the way that they're supposed to. But they noticed when they gave it to people that only a few very specific blood vessels were actually dilating. And so it was causing blood flow to go to one very specific area. But originally, Viagra was actually meant to be a heart pill. That was its original intention. And then they found something else, and it has probably made a lot more money in a very different side of the industry. So that's an example of vasodilation, right? Vasoconstriction is exactly the opposite. That is actually where your blood vessels constrict in order to limit blood flow. So again, when we talk about like exercise, right, which is a fight or flight system, your body will send blood to your skeletal muscle, and it will constrict blood to places like your digestive system. And weirdly enough, it'll constrict places to certain parts of your brain. I'm sure you guys have experienced a little bit of gym brain every now and then. I've definitely like worked out really hard and used my nervous system for pretty much exclusively lifting weight. And then afterwards, I just feel a little foggy sometimes. Things aren't working quite as fast. Once I cool down, though, everything sort of returns back to normal, and I feel a little bit quicker. They have actually done studies on that, and they've noticed that, like, sad to say, you're a little dumber like when you leave the gym for a few minutes, and then it kind of comes back pretty quickly, which is actually probably part of the reason why exercise has actually been shown to be very good for overall, like, not only emotional, but also like logical intelligence. One more reason why we actually want to get kids to exercise regularly. Yeah, in the short term, you're going to struggle with some math problems, but once you sort of cool down and return back to normal, you might find you have some inspiration. So all of this is going to happen due to like the contraction of certain parts of the body that, trigger blood to sort of travel where it needs to go. So for instance, like squeezing the calf muscles, again, it's going to drive blood back to the heart. And that can actually really help with blood flow. So there is also, like, when we're looking at your overall pulse, right, we are looking at like whenever your left ventricle squeezes, right? So as you place your thumb along like what is called your carotid artery, right, you can feel blood go rushing past it. That's your left ventricle squeezing. So you're feeling that like sort of wave of pressure. And obviously that can be affected by a lot of different things, body size, gender. Women tend to have like smaller, thinner blood vessels. So sometimes they're harder to feel. Like if you're using like the 2-finger method, it's not going to be quite as easy sometimes. So like this is one of the reasons why it's always encouraging to tell your clients to just wear a straight up heart rate monitor, Now there are two types, just taking a second here. There are two types of heart rate monitors out there. There's this kind. Oh, of course, the freaking thing is on. Oh my God, that's so annoying. because I pulled it off my wrist, and then there we go. There's this type here, which gives you like the green light. The reason it uses green is because that's sort of opposite on the color spectrum as like red. And so it's very easy to, it's actually counting how often red blood cells are rushing past the light. And so that's how heart rate monitors that are on your wrist measure your heart rate. It's pretty good, fairly accurate at low heart rates. However, when your heart rate gets really fast, it kind of all looks like one continuous flow. So oftentimes this misses a few beats and gets less accurate the higher your heart rate is. If you want a super accurate heart rate monitor, use the chest strap type, and that is actually going to sense when there is an electric impulse from your heart. So every time your nervous system tells your SA node to beat, the chest strap monitors are going to pick up on that. And so you want a super accurate heart rate, wear the chest strap. And that can be a really great way to kind of monitor that if you are like exercising at specific heart rates. So lastly, looking at blood pressure again, right? The pressure, your blood pressure is going to be the amount of pressure pushing on the walls of those blood vessels, right? So we've got the 120, that's the squeezing of the heart. And then we've got the 80, that's the relaxation of the heart. Because even when your heart relaxes, there's still some pressure there. Ideally, that is what we want our blood pressure to be. Now, obviously, the further blood gets away from our heart, the lower and lower the blood pressure is going to be, which is why we don't measure blood pressure using like veins. We use arteries, right? Particularly the ones that are pretty close to our heart. So we measure it right here because the pressure is pretty much the same, right? So you are going to have two numbers there. You are going to have your systolic blood pressure, right? That's going to be the amount of pressure during the contraction. We call that systole. Ideally, it's around 120. And then you have your diastolic pressure, which is during the relaxation of the heart, where ideally it should be around 80. So normal blood pressure is about 120 over 80. Hypertension is going to start at 140 over 90. This is what we call high blood pressure. Now, here's the thing. Your blood pressure goes way higher than 140 over 90 when you're exercising. Like if you're doing a deadlift, what is it like one of the highest blood pressures ever recorded was during somebody doing a deadlift. 370 over 360. That is crazy high, right? That means there's a lot of pressure. Now, here's the thing. That's not a big deal when you're exercising. In fact, we need that pressure to get blood to move in the direction we want it to. We're in a high blood flow, blood pumping situation here because we're working out, right? It's when it's 140 over 90 when you are at rest that it's a problem, because that indicates that it's chronically high all the time. That tells us that your heart's not functioning the way it's supposed to. That's why they pay attention to blood pressure. Because if it ever gets too high, passively, it might not get back to your heart someday. And then your heart won't be able to pump blood to everywhere else. And that causes like a lack of oxygen. We know we need oxygen for energy production. It's what keeps our cells alive. So there's a lot of things that can raise your blood pressure. It can be vasomotor changes, it could be the blood vessels dilating or constricting. It can be the elasticity of your blood vessels. One of the reasons why I like high sodium diets are considered not so great for us is because it hardens our arteries, which makes them stiffer. It could be the viscosity of your blood. Too many red blood cells can actually be really dangerous. That girl was in the Olympics was blood doping recently, right? The reason that's so dangerous is because it increases the viscosity of the blood. It makes it thicker and harder to pump. Not good, and total blood volume, if you're dehydrated, your blood's going to be stickier. If you're overly hydrated, well, now you got more blood, because blood is different from red blood cells, So ideally, we want to stay well hydrated. We want to make sure that we have a good concentration of materials, and we want to make sure we can dilate and constrict our blood vessels the way we're supposed to. And one of the ways we monitor that is just by looking at simple numbers to see if they're within a healthy range, 120 over 80. So there are a lot of, there's also low blood pressure. That's also dangerous. You've experienced low blood pressure before, by the way. If you've ever been like just sitting on the couch, you've maybe been there for a little while, been like super relaxed, and all of a sudden you like jump up to like go do something. You're like, okay, I gotta get my day started. And then you jump up and all of a sudden you feel like you're gonna pass out. That's low blood pressure. It's because all your blood didn't have enough pressure to like deal with this really fast movement all of a sudden. Very similarly to what we started with today, with the G-force simulator causing blood to be over there when you're over there, right? And then high blood pressure, that's really bad. There's also essential hypertension. That's what happens when you're exercising, right? So these are all the things that increase your blood pressure, right? You know, here's a normal artery. We build up a little fat on the inside. It gets thicker and thicker until eventually blood can't travel. That is going to cause an increase in that pressure. Lost Julio, I think. Now there's also like aneurysms that can sometimes happen. If blood starts pooling in one area, it can cause the blood vessel to stretch. If this happens in an artery, that's extremely, extremely dangerous. This can burst. And if that does, that means that you now have an open vascular system, which means it will cause dramatic drops in certain places and blood will start pooling. It cannot get delivered to your brain or your heart, and it can kill you. It's really dangerous. We have varicose veins, where blood is basically pooling in the veins and causing them to stretch out. And, you know, there's all kinds of other blood vessel problems out there. But like I said, we're not going to spend too much time on those diseases. So that's what I got for you today, guys. For some of you, that was a big review. I know some of you guys, it's your first time seeing this, but how are y'all feeling? Any questions today? Anything unclear?
No questions. I just this is in our membranes, right? I would assume this is in the body, the big black one, right?
It is in the membranes, yeah. Chapter, let me open that back up. You're gonna look at chapters. Sorry, 1 second. Chapters 14 and 15 of the memoirs. So we're going to do a big jump forward in memoirs. This will also be reviewed in your NASM, chapter 2.
Okay. Okay, then I'll do some reading. I'll do some more reading then later on.
I'll let you know what chapter when I open the NASM slides. So, all right, guys, that is about it for today. Let's kill the recording and